Gentlemen, welcome back for another round. This is Mr. Doolin. Thank you for tuning in. Today what we're going to do is we're going to take a look at the mole. This is our first kind of mentioning of the mole in PreAP chemistry, and it's a term that, believe it or not, is something that will never go away from us. In all of chemistry and all of science, we deal with this quantity called the mole, and right off the bat, I'm not even going to try and beat around the bush. 1 mole is equal to 6.02 times 10 to the 23rd particles. And that's the punchline of this. The mole is actually just a term that describes a number. Like if I told you I had a pair of something, you're going to say, oh, he's got 2. If I have a dozen of something, you're going to say, oh, he's got 12. And so what I'm telling you in chemistry is that if I have a mole of something, I've actually got 6.02 times 10 to the 23rd of those particular things. All right? And then let's just give you an idea of what this number actually is. So this is 6, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. All right? And so if you actually look this number up to figure out what it is, it's actually, I think it's 602 decillion. I bet you've never heard of the number decillion ever in your life, because I'd never heard of it until I looked it up, right? I've heard of a billion, I've heard of a trillion, I've heard of a Google, but I've never heard of a decillion, and that's actually the size of what this actually is. So let's get into, since we understand it's a really, really big number, and by the way, to give you an idea of the magnitude of what size of a number this is, let's use a couple of very visual examples. Like, for example, if I were to take those large marshmallows, you know, the kind that you actually use at like a camp out, those really, really big fat marshmallows, right? If I were to take those marshmallows and just put them as close as I can to each other all over the face of the earth, right, and then start stacking them on top, we would have the earth covered in marshmallows up to 18 miles in the air, right? Just 18 miles high of marshmallows stacked all the way around the earth. We'd be a big white ball of earth of marshmallowness, all right? The other very visual representation is if I had dollar bills, and what I was going to do is I had a mole of dollar bills, right? If I had a mole of dollar bills, I could actually stack these dollar bills up from the earth, the surface of the earth, to the moon and back. I could do that with dollar bills 80 billion times. I could go back and forth from the earth to the moon 80 billion times if I had a mole of dollars. And then the last visual representation I'll give to you is if I had pennies. If I had a mole of pennies and I wanted to give pennies, an equal number of pennies to every single person on this planet, right? We'll assume we're somewhere between 6 and 7 billion people on this planet. If I had a mole of pennies and I was going to give pennies to every single human being on this planet, right, and just equally distribute them, we would have people with almost $1 trillion worth of pennies. Every single person on this planet, if I had a mole of pennies and I wanted to give them away equally, everybody would get almost $1 trillion worth of pennies. All right? So what I'm trying to get apart to you or impart to you here is that this term, the mole, is a really, really big number. All right, and so now what we want to do is we want to figure out where did it come from, or where you want to learn where did this number actually come from. So in 1961, scientists actually chose to use the carbon-12 atom, right, the carbon-12 isotope, if you will, as the standard to determine all other atomic masses. So carbon-12 becomes our standard, and it's just because carbon's one of the most abundant elements on the earth, right, that they chose carbon-12. And so what they did is they defined carbon-12 to have a mass of exactly, and the term exactly becomes important here, of exactly 12, actually they did 12 AMU, right? Because we're looking, and AMU is atomic mass units, and so what they're saying is that a carbon-12 isotope has an AMU of exactly 12, all right? Protons plus neutrons, 12, right? 6 protons, 6 neutrons, exactly 12. And then what they said is that all other atomic masses were going to be relative to this carbon-12. And we do this using mass spectrometry, and if you want to get into the hows and whys of that, you can come on to class and we can have that discussion there, but I think it's a little bit more than we need at this point. All right? And so what they did is they took carbon-12, they made it the standard, and so what they said is we know that one atom of carbon-12 has a literal mass of 1.99265 times 10 to the negative 23rd grams. That's how much, if I could hold one carbon-12 atom in my hand and put it on a scale, that's how much it weighs. And again, we're using mass spectrometry to figure this out, right? And so what they said is, if we're going to say that carbon-12 has an exact mass of 12 AMU, then if I had a mole of substance here, right, it would be exactly 12 grams. So what we did is we took 12 grams of carbon-12, we divided it by the mass of one atom, per atom, right? And what that leads us to is Avogadro's number, and that's this 6.02 times 10 to the 23rd atoms of carbon-12 in 12 grams of carbon, right? And so this number actually has now been called Avogadro's number. It's Avogadro's number, and it's a constant, right? That is 1 mole of substance. If I had 1 mole of carbon-12, it would weigh exactly 12 grams. And so what we do is you look at the periodic table, and y'all have seen those masses, the atomic masses on the bottom of the periodic table, and nobody's ever explained to you exactly where we get those from or what those mean. But what we know is that all of those particular elements, those are atomic masses. Those are the mass of 1 mole of that particular substance. So for example, if I look at hydrogen, you're going to say hydrogen has a mass of 1.008 grams. Well, now what we're going to say is that hydrogen has a mass of 1.008 grams per mole. All right? And any other mass up there is now a grams per mole relationship. All right? And so where are we going to go with this? You got it. We got some units. We got a fraction looking deal. You should be singing dimensional analysis in your head. We're actually going to call it stoichiometry. We'll get there. But essentially what I'm going to do is just tell you, we're going to take this amount that we're going to call the mole, right? That is 6.02 times 10 to the 23rd particles, and we're going to relate it to mass in grams. And that's grams. And then we're also going to be relating it to the particles, right? How many molecules or how many atoms do I have present at any particular sample, right? And this becomes important because reactions occur at the atomic level, ladies and gentlemen. I have atoms that actually react with each other, but I can't weigh out atoms, right? But I can weigh out moles, I can weigh out masses, right? And then the other thing that we're going to relate it to here is volume, and that's going to be in liters, right? So I can take this term, the mole, and I can actually relate it to things that I can use and function with in a laboratory setting, because I can measure a mass and I can measure a volume, all right? Particles, that gets more on the theoretical side, but I can measure out grams and I can measure out volume, all right? And so what I'm really trying to get across here, ladies and gentlemen, you do need to understand the relationship that 1 mole is equal to Avogadro's number, which is 6.02 times 10 to the 23rd particles. We definitely need to know this relationship. This is going to be one of those conversion factors that we're going to use in dimensional analysis, and this is your first one. This is a big one, ladies and gentlemen. 1 mole is 6.02 times 10 to the 23rd particles. And think about it. We knew atoms were really, really small, right? And that's why there's a whole lot of them in just a small amount of mass, okay? All right, ladies and gentlemen, if you have any questions, make sure you get them down. I'll see you in tutorials. Other than that, I'll see you in class.